Thank you. Welcome everyone to another Rolling Scope School lecture. This will be dedicated to basics of HTTP. We'll touch on the HTTPS as well, and also start learning what's the REST and RESTful APIs are. And as always, when we talk about HTTP, it's all about protocols, and it's always easier to see how it works and what it is when you actually have a simple example. So when you want to know what is the protocol, the kind of web page that you're looking for, it's always at the start of the URL. So when we talk about HTTP or HTTPS or WebSockets or even file protocol, it's always at the start of the URL. That's good to know. And as always, we'll start with a bit of history. It all started in CERN a couple of years ago, in the 90s actually, when the creator of World Wide Web, that one guy, Berners-Lee, he decided to create the notion that will allow us to access different resources on the web. And he created universal resource identifiers and decided to implement it in a way that the HTTP works nowadays. And overall, yeah, by doing so, he created HTML and the whole World Wide Web, so to say. So somewhere in the 70s, very smart people created an abstraction on top of the whole networking stuff that is behind the scenes going on in our everyday lives. And this abstraction is called Open System Interconnection, kind of a standard for how the things implemented on the physical and as well as the software level. So when we talk about like receiving bytes or like sending bytes, it all comes down to actual physical processes, and the OCI model it just tells us what happens from the moment we click somewhere or we send the request to the actual bits and bytes and down to the actual electrons and the electrical signals that travel through the wires that interconnect the whole world. So that's the whole thing, and it's always either in the case of transmission, always from the top to bottom, from the application that sends the request to the actual physical layer, those wires that somehow interpret the data it wants to send, and it actually sends it. And then as well, on the other end, when we receive the data, it goes vice versa. So to create such a model, we need some kind of a way to describe how the whole thing works. And some of the people, some of the abstractions that were implemented on top of that included the TCP/IP, a bunch of nonsensical words, but at least understand that the TCP/IP, it's all about application, presentation, and session thing. So without actually going into any other layers, into any hardware, just when we talk about TCP/IP, it's always about the networking behind the scenes of our applications. So that's enough of the abstraction for the beginning of introduction to the HTTP level. So on this model, we don't see any HTTP. We actually see the TCP/IP, which is a bit confusing because we don't understand what's going on. And the TCP/IP is somewhere on this level, so on the level of bits and bytes and how to create those packages and actually transport them somewhere. But where is the HTTP located? So an HTTP is the thing that is behind this huge box, which is our application, maybe some of the session, is also connected with the HTTP. And HTTP is just a standard to construct the requests in some of the way that the levels below that in the TCP/IP model understand them. As always, we start with a bunch of releases or versions of HTTP. Current one is HTTP 2.0 with some of the improvements at the moment, but still, this is the latest and greatest. And going back to the HTTP, when we talk about the model, we don't talk about beautiful pictures, we don't talk about abstractions. We actually talk about some of the ways that the work, that the connection, that the request and response things organized, and there is an important notion that is behind the scenes, which is a triple handshake. And the triple handshake can be abstracted without going into much of the details, as several times going back and forth between the client and the server, in this case the sender and the receiver, to establish that connection. This is a part of the TCP/IP model. When we always, when we talk about network and receiving something or sending some data, we need to take into account some latency. And latency is a term, without going again into much of the details of the network and how the bits and bytes work under the hood, it's just the time that it takes for our client, for our computers to go to the server and back, with all the layers of abstraction, all the internet service providers, the cables, because we know that the cables kind of influence the whole thing. So all this time that it takes for our requests to reach the server and maybe back, or the server events to reach the clients, this is the latency. We also have this thing called round trip time, which is a part of latency definition. So just for you to understand that there are some notions that describe that time, how much it takes to go back and forth. That's why it's called round trip time. So when we talk about latency and network, you'll come across some of the terms like DNS, which is the domain name system, which is actually the way the whole internet works. And that's how we know where to send the data. So if we look at the previous picture, for us to go through all these layers of abstraction, maybe that could be implemented at different levels and could be implemented in different parts of the world, and the server could be in different part of the world, we need to know exactly where to send the data, as if we would connect it through a cable. But since there are lots of cables, we need some kind of a service that helps us to point into the right direction, and the direction is that IP address, either IPv4 or IPv6 that is adopted currently. But to use this address to send all the requests, even for developers, that will be not really kind of comfortable to do that, because it's not readable, it's not human readable. But computers, they need that address. So domain name system as a special service that sits somewhere in between our computers and the service is the actual thing that translates that human readable request that we send to the actual location of that server on the web. That's how it's happening. So we, as a DNS client or just a client, before we send any useful data, we need to do that thing called DNS lookup, which is just a request, a special kind of request to the nearest DNS server to actually receive that location where we need to send that data. And after that, we can do the actual requests. So if we take a look at the picture, every time you do the request, a new request, I'd say, you have that little thing, little delay. That's where the DNS lookup happens. So if we take a look at the actual URL, we are requesting the static HTML file or something from the dnhume.com / which is the root folder. Happens the DNS lookup. Then if we look at the actual 6 requests, which is at the same root domain, but for the different resource, we already know that domain name. We know where to send our request for logo.png. And that's why the request takes like 5 times less time than if we were to do that DNS lookup in the first place. So all this stuff about DNS lookups, some kind of connected things, some of you may encountered already when you had to join the project, for example, and edit some of the files or some of the DNS to the IP address information to this location on your Windows system on the host.config file. That's where, like, typically a custom domain name like mapping happens, so that our computer actually, without actually sending any request to the DNS, knows how to access some of the resources because they can be hidden. So there's lots of stuff you can look into when it comes to DNS. So good thing to look into if you want to know more about the DNS lookups. But that's the whole thing happens even before you send any requests. So that's why we're covering it. So because without knowing what DNS, what maybe the TCP/IP, the OCI model, the actual discussion of the HTTP would not be possible, because it's all built on top of that. So the actual HTTP stands for the Hypertext Transfer Protocol, and as you can see from the same guy who invented that, that's an application level protocol. And going back to the OCI model that we looked into somewhere up there, that's where the HTTP lives. So not with the transport network or data even link model where the TCP/IP lives. The application layer is the one that the HTTP uses. So going back to the definition, application level protocol, that means that this is just a definition of the way we need to construct our requests and expect our response to be constructed with, so that the levels below that inside our computer, the TCP/IP model level layers below that, understand what we mean and where to send out data. So by saying that we're constructing some of the request information, I see that when we have some kind of URL, even when we not explicitly constructing anything, even if we just go to the google.com or some kind of host, we constructing a message in the background that says the protocol, the HTTP/1.1, the URL, the actual URL that we're accessing, the method, maybe the host with a port, etc., etc. So there's a whole like list of things that every time we do a request, we kind of constructing on fly, so that all the layers can understand what we're doing, actually send the request, and the server decrypt that request, so to say, and respond back to us, constructing the same message to us. So the P in the HTTP stands for the protocol, which is a way of constructing those messages and expecting the messages to be constructed in. So the evolution of the HTTP, not really interesting nowadays, but at least you can understand how it happened. We have almost the same things that we're doing today, but we have some additional features. Anyway, as you can see, we are using the same method, which is I want to get some of the resources at this address, as you can see, without the AP, the DNS. And then if we go further and further into the future, we see that we add more and more stuff, but still remaining the same of the methods and the resources, like the format, the protocol format that we use remains the same. There are a bunch of stuff that we need to be aware of when we say we do HTTP request or we receive a response, HTTP response. Maybe you're familiar with the connection keep alive or something like that. So when we look at the way that the OCI model works, or the whole thing works, where we need to make requests, that triple handshake, as I mentioned, where when we actually make every request, the server processes something and then responds with the information that it has that we requested, hopefully, and then the whole thing ends. That's the typical thing. So triple handshake, the actual request, this green line, the processing, and the response. Nothing too dandy. But according to the first iterations of the HTTP protocol, that was the only way to do that. Almost the only way, but still. But we could optimize that, and we were thinking about the ways to optimize that. So it was the separate requests, as I mentioned. And when we added the keep alive option, like configuration, or I should say header, instead of actually going back and forth doing the same triple handshake, like, hey, I'm the same client as you did before, we can actually send some stuff along the way with our first request to say to the server that, hey, if you receive a request from me the next time I go to you for some of the stuff, don't ask me to authenticate again. It's like the session that we're all familiar with when we access some of the data. So you just type your login and password and you're able to access the site without actually retyping it every time you go to that URL, because it's stored in the browser. So the same comes to the server. Server is just a computer. So with a keep alive connection header, we can say that, hey server, I want you to remember me. There's also some kind of like HTTP pipeline. Really good stuff to look into if you're interested in. But we move on. There are some limitations that apply to the HTTP protocol. One of them is a 6 connection limit per origin, which means that we can actually initiate lots of parallel requests to improve our timing, because they all take some considerable amount of time, but still, if we make them consequently, that will take even more time, so we're parallelizing the whole thing. So there are some limitations to that, so that the server that work with that protocol and the underlying infrastructure and the OCI model could handle the whole thing. So for the 101 features, I say we have like pool protocol, stateless and scalable, simple, as always with those technologies. But the key word for the whole thing is stateless, I'd say, in my own opinion. Because we want to, instead of actually, as I mentioned, making a connection to the server like stable in terms of the establishing a link so that the server knows who we are forced to go and make requests every time we do anything, as we mentioned here in the picture. And that means that we can do that for any server, and the server can respond to any client without actually knowing them and without actually keeping some track of information who accessed them and what they need to respond with. So that's the whole thing about stateless. The request headers, that I mentioned, keep alive, or the content length, the URL, so that the server knows what the URL was before we got the DNS translation. User agent, also one of the headers, and headers, they're just additional configs apart from what we need and what we're sending to the server. So as usually with the requests, we're specifying where to send it and like a package, like address and the package itself. And if you can think of the headers as additional information that you type in the Amazon application, like live at the door, or maybe send, if I'm not home, give it to my neighbor. So headers are like additional instructions for the delivery person. Yeah, there are lots of them. Keep alive is also one of the headers, possible headers. There are a number of ways to set those configs, but the headers are the most likely place that you will send the configs for every request. The response headers are the same. It's like the Amazon gives you information on when the request comes, what to do, who will be the delivery person. Apart from your package that gets delivered, you receive some additional information about how it's getting delivered. So you will see for your package that, for example, content type text HTML, so that you as a client know how to decode the message. Also with the gzipped is some kind of, if you're familiar with the, zipping of files, that's almost the same principle. You zip before you send, and then the receiving end, you unzip the whole thing. Content length also for the checks if the content was tempered or not. And yeah, again, keep alive. As we request the keep alive, so it needs to respond with a keep alive, that it's agreed to do that. Apart from those instructions, we usually, when we even do that thing in real life, we say we want to receive stuff or we want to send stuff, like whether you like receiving stuff from Amazon, you're saying that I want to receive something, or if you're posting a message to a friend somewhere using a Royal Post or something, you go and you actually give that envelope to the post office and you send, hey, I want to post it. I'm not here to receive. That's kind of the HTML meaning. And there are a bunch of them: options, get, head, post, put, delete, trace, connect. All of them are those words that you see every time you send something. So even if you're sending to the same location, to the same URL with the same body, just by changing the method of like, hey, I need to get the information, here's additional stuff, or I need to post the information, you can do almost the same request, but with a different intent. So HTTP methods are intent. I want to put stuff, I want to create stuff, I want to have some options, they look at some options, I want to just get stuff that I know is there. The server can respond with additional semantic meaning without actually sending the response itself with the content and etc., the actual nitty-gritty stuff. It can actually also give you additional information whether everything went okay or not. So we've got a bunch of semantic status code. You can think of them as the way of Amazon when you receive a package, says, hey, delivered, or hey, you were not at home, redirected, or client error even, or maybe you give us the wrong address, we couldn't deliver that, or there was a problem on our side, sorry. So a bunch of codes, they have different additional meaning. All you need to know to go and explore the HTTP and how the requests work is that there are like several groups of messages. 200, as you know, is a successful message. 404 as not found, or 400 as unauthorized. 500 as something went wrong, internal server error. They're just telling you where the problem lies, whether you did something wrong when you send the request, whether the application server has some internal errors, or whether you're sending to the wrong address and, hey, here is the new address. Same way as the real life works when you use the post office, or maybe, yeah, success. When the server actually responds to the errors, we as clients on the client side and browsers in our application that makes those requests, we can display different types of information depending on how we want to approach it. Whether we want for our clients to suffer without knowing what to do, it's like not displaying anything meaningful, some kind of gibberish words for a common folks, or we actually want to display something meaningful and even leave them a way for them to connect with us, giving us additional information, maybe filling a complaint or helping us to know when that thing happened. Maybe some jokes also. Again, with the 404, where the client is responsible for the error, without actually telling them what to do, we can actually tell them, hey, something went wrong, for example. So at this point, we take a break. Maybe you have some questions before we move on. I shall ask questions myself. If you know what the moves permanently would mean, when you actually have the request and response. Does anybody here can actually say what move permanently would mean? Okay, let me check the chat. Yeah, moved permanently, meaning that something changed and we have information where the request should be sent. For example, when Facebook changes the URL or changes the subdomain to the www.facebook.com, we know where to send the requests, and that could be useful not for common users, but especially for the SEO optimization. So search engines, those applications that look into URLs trying to display something. When we, for example, paste the URLs into our chat and we see some kind of additional information with a picture, that error or that like status code can actually help that logic behind the whole thing of displaying some additional information to work properly. Okay, there is a way for us to store additional information in our browsers when we receive something from the website or from the web server, and that is the funny name thing, which is cookies. Cookies, there are a bunch of types of different cookies. It could be session cookie, it could be persistent cookie, it could be secure cookie. They all have different applications inside our browsers, there's a whole logic with the network. We can see them in a special tab in any browser that we use. It would be under resources in the cookies. There are a bunch of ways to send those cookies. If you don't understand what cookies are, what they're used for, just think of the whole stateless nature of the communication. That we make a request to the server doesn't know who we are, it responds with something. But what if we wanted to, hey, server, this is me. I talk to you again. It's not just about the connection that we need to keep alive, but I'm the actual user. My name is Dmitry, for example. Give me information related to only me. And that's where we send the cookie along, like, hey, be nice, please. So there are a bunch of ways to do that. It's a document.cookie to tell our browser to get that information or store inside the cookie some information. We could be in the response itself, set cookie, and this is a key value pair. Plugins also able to do that. And again, we can do that manually as we did with the DNS lookup thing. And again, question time. Do you think there is a way to set the cookie in some different way? How can we actually store something somewhere or send it along the way? What is another way for us to tell the server that we need some specific stuff? Can somebody answer that? Ilya, maybe you know the answer again? Okay, silence is my answer. Okay, look at the URL that I'm actually using. There are a bunch of things that is written in every URL. It's not just the address of the actual website that is currently responsible of giving that information to me to show you the presentation. But actually, I'm sending some additional requests for the slides from the school folder, from the HTTP. I need 14th presentation and the 5th slide. And the server is able to pass this information, parse in terms of like looking into the URL and understanding different parts of it. And that's exactly what we when we can store that information apart from HTML itself that is getting sent along the way. So the same as we storing some information in the URL, we can store the same information in the meta tags. Remember what I told you about the SEO optimizations that could be improved in the previous slide with the status code, the correct status code? That's the same meta information or like semantic information that we can specify in the HTML. That is a wrong slide. Okay, so at this point we can actually look into not the vk.com that the slides suggests, but we can go to google.com, for example, and look into the network tab. And you know what? Maybe we can go to what can I show you? Could it be okay? Let's go into GitHub. So every time we make a request to the GitHub, because Google has some stuff that they do apart from the HTTP, that's why I wanted to switch to GitHub. And if I refresh the page, in the network tab, I see lots of stuff going on. Not all of them are HTTP. It could be other stuff that could be used under the hood. But anyhow, as you can see, the first thing that we hit is the request for the page itself. And I know that this is the request for the page because I know how the whole thing in the web works, where I need to see some stuff on the page and I request that stuff, github.com, and at the root folder of the server that holds the github.com, there is a file. This is exactly the file, how a file looks. And as you can see, not all of the stuff is inside that file. So if we take a look at the response itself, it's a huge HTML thing with all those meta tags. You know that stuff already. Some of the parts require additional information to be available, and there will be additional requests somewhere here. Maybe some repositories or something like that, or stats to the GitHub API, yeah. For example, maybe there is something inside of there, maybe dashboard feed. Yes, additional things that we look into as additional static information from the different URL. All of that is constructed in a way that the HTTP describes. We have the request URL where we want to receive that stuff from GitHub. We have a method, we have the status code that we receive from the server. We have some additional response headers and request headers that we send from the client, and then the server sends back. That there is an encoding, gzip, the control, some security stuff, content type to say that it's actually HTML compared to, if we look at the SVG, we'll see that the content type is a different one, image SVG. That's like an additional information that the server provides to us apart from the actual content. We also can see sometimes when we post something, for example, when I go into, let me go to the repositories. Maybe we'll find some kind of stats. Yeah, so when we post something to the API to receive some stuff, we want to specify some of the body that we want to see. For example, some of the information that we send along the way in the request payload, because that's the post method that we're using in the HTTP. And in the post method, we can actually send something along the way saying that, hey, web server, take this information and do something with it. As you can see, it doesn't respond with anything meaningful, but at least. So this is where the whole networking lives. So that you know, later in the course, we'll discuss how to make those requests happen. But for now, we go back to the presentation. A bunch of stuff that we mentioned already, like client server clients, you know what clients, a typical client is, like a browser, web browser, maybe some terminal application. But for web services, or servers, I'd say, we have different solutions. We have gloriful Node.js, but also before that Node.js thing, and even the latest and greatest Nginx, maybe like the popular one that developers know after the Node.js. We had some internet information services from the Microsoft team. We have Apache, those who tried developing with PHP. Remember that PHP MyAdmin that is getting deployed on the Apache web server. Jetty is another server that can respond with that, and there are like actually a bunch of them. They all can respond to our requests. Something I didn't mention before, or I touched briefly, is that with some of the approaches like cookies, we need to provide some additional information so that the server actually gives that cookie. As you can see, this is the cookie that it gives us. And one of the ways to organize the whole workflow with a cookie, with the authentication, by sending our login password and username in the post request to the server, what actually goes into like deciding whether to give us that cookie or not. And every time we make a request with that cookie that we saved somewhere in the browser, it knows that this person is the same as this one because this is the same cookie, and that's the whole thing. And we call this process a session establishing process. Cookie is one of the ways to do that, actually. So without going into much of the details, session is all about the server not like remembering us personally, but recognizing us when we send the cookie with every request that we make to that server. And again, question time. Let's imagine we're making a request to a bank and responds with OK, but there is someone along the way listening to our requests. How do we protect client and server from those third-party hackers that are in between, so-called middlemen? Any suggestions? Maybe in the chat, or you can unmute and tell me like that. Okay. HTTPS. Okay, good. Maybe you can elaborate a bit on how exactly HTTPS protects us from those middlemen. Certificate. Okay. And by certificate, you mean like what is the logic behind having a different protocol and what protocol does for us? Like, why do we think that one of the protocol is better than the other? What should we do with the information that we're sending? We cannot just hide the information, aren't we? So that the certificate that we receive or that we use, you know that thing, the untrusted connection thing, that is where the certificate comes from. But the first tip was actually public keys. And the answer is, certification center, but that certification center should be used as a way for us to prove that we can encrypt stuff. So, and going back to the OCI model, since we know that the application layer is the one that actually holds that HTTP protocol, that holds the rules to organize those requests, and we know that the TCP and IP model specifies that the transport and network layers is the ones that are used. In between them, we have the kind of session layer, which is, in my opinion, a bit confusing name for that. But anyways, it's where we can specify additional rules of how the request should be handled, and we call those rules, well, in the old way, it's SSL, or modern way, TLS. And that's actually what the certificates and the public and private keys rely upon. They rely on this layer, the whole thing with where we use those public and private keys and the certificate to somehow hide the information from the third party. It happens at the session layer, kind of. You can think of it this way. But if we were to answer the whole thing about how do we hide stuff between the client and the server without actually compromising both of them, without actually letting the anonymous guys to see our information that we're sending, we cannot hide the request. There will always be people who will see the request coming and going, but we can hide the information inside the request so that even if they like hook in between ourselves, they won't be able to use that information that we're sending because it will be just a bunch of gibberish and rubbish that we encrypted or somehow obfuscated with the use of certificates and public and private keys. That's a high-level idea behind it. So not hide, but encrypt and obfuscate so that these people are not aware of those bits and bytes that we're sending. And we slowly but surely came to the REST thing. not like actually resting from a long lecture, but to the REST API. So REST is one of the ways to organize the web services, or maybe application services. Some people may know that. It's not about how they talk to each other. We discussed it with HTTP, so that is covered. So clients, our computers, can talk to other computers, servers, and that's covered by HTTP or HTTPS. But how does those clients are actually organized inside? What is the actual URL to receive this first slide? Should it be slides school? Should it be slides 1 or slides give me the slide, the next slide? The way of organizing resources inside of the server itself, and the way it expects us to ask for those resources, is one of the ways that we're discussing now. So REST as a representational state transfer is the way to organize that. Before we had remote procedure calls, which is like our client computers telling the web services to do something of like, hey, do that, or hey, do this. And we send that information in a way of XML, extended markup language. We also had some SOAP thing that is kind of an extension on top of the XML and RPC, but using a more stateless approach. And somewhere along the line, we introduced the REST API approach, where we're basically sending, the REST API approach will basically send less information, but in a more strict way, without actually stating or constructing some of the requests. It's a more free way to organize the communication on the service level. So remember, the REST is not about how the data transfers in between the client and server. It's more about how we structure the server itself and the information inside of it, and how do we ask for that information. So if we look at remote procedure calls using XML, it was something like that. So XML syntax, really close to the markup language, like hypertext markup language that we currently use. But the remote procedure call is actually what we do in the server. So the clients, like our computers, had to know what functions, kind of, or methods or procedures are available on the server side, and they are the ones who decide when to call what values to pass. Kind of really, really tight coupling between the client and servers. And the response was not that of a big deal, I guess. Yeah, my presentation is a bit broken. But anyway, as you can see, we received the same format of XML response. SOAP was a bit of a different way. We introduced a more loosely coupled approach, but in the same like XML look-like way. It even states that. We also send like some additional IDs of specifying exactly what we need to do, but we actually don't know which of the function is going to be called inside of the server itself, and we receive it in the same XML format. So a bit of verbose again, so lots of information, lots of rules how to construct this. So and the actual useful information for us is this one. So we can live without anything here except for the product ID itself. So we had to come up with something a bit less verbose, and that's where the REST came. So with the introduction of the HTTP, we know that we can use some kind of URL structure like resource links that could state exactly where to go, what part of the state of we want, and which exactly piece of information to send back. And yeah, we specify the GET request. And the response could be as simple as a few lines of code, and maybe even a few lines of response. And there are a bunch of ways that the REST could respond to us, either with the actual HTML, or it could be just a bunch of data. So REST, as a way to organize our backend resources, is HTTP based. It is client oriented, meaning relies heavily on the client in terms of the improvement of performance. It is stateless, simply meaning that as the same way that we did with the HTTP, we say that the server should be able to respond to any of the requests, no matter who sent them, if they are constructed correctly. So whether I'm the one who constructs this URL or you're the ones who construct the URL, the server needs to respond in the same way. So it could be cacheable because of that, because the information I receive in the end from the same URL is the same as you would receive if you construct the same URL, so we can cache the result somewhere, maybe close to you or close to me. There are a bunch of stuff that is improved in terms of the SOAP compared to the SOAP approach. Some of them I already mentioned, which is, for example, HTML-based protocol, which is SOAP, and the REST is an architectural style protocol, which is like a way for us not to say how the request should be constructed, but where exactly should we ask the information from, which type of thing. And also compared to the SOAP and the response that we receive in terms of the special markup language that should be passed in some special way with using some special things. In REST API, we usually have JSON data, which is easily passed by JavaScript. Luckily, we know JavaScript, so that's a really good thing. So going, in the end, REST and JSON we're so used to using is one love, as I should say. One of the ways that the REST is constructed, or the REST is like designed, as I mentioned already, is that it's stateless. And the other side of the stateless notion is that REST requests and responses should be idempotent and safe, meaning that no matter who constructs the request, the response should be the same, meaning that if a single client, even if a single client constructs the same request number of times, the response should not change. It shouldn't be the way that some kind of counter behind the scenes, counting when to respond with the actual information and when to be a bit sissy. So idempotence is stateless in between the number of times that we request the information. Safe methods are methods that could be safely cached because of their idempotency and because of their stateless nature somewhere, so that we can actually move the information a bit closer to the clients. There are a bunch of useful tools that you can use to organize or analyze the network. I already showed you one. It's the actual DevTools, but the functionality, well, it's reach, but it's a bit limited. So you can use other tools. The presentation would be available to you. So you can click on a bunch of links. One of the most famous one is the Fiddler, I think. Netcat is the one that most of the network engineers use. It's a more terminal-based network tool, as well as a telnet also. Wireshark, it is used by developers and maybe by the network people, but if you do some kind of, in the future, some kind of pen testing, penetration testing, Wireshark is the one app that you're going to use a lot, because it allows you to look into the packages, even fiddle with them, haha, Fiddler, and do a bunch of cool stuff as well on top of the whole thing. So yeah, it might be useful to you. There is a bunch of commands that we can do. So ping, tracenet, ipconfig, and netstat. They're really useful because of you might be familiar with them already, but anyways, if you just open the terminal and, for example, ping Google, just like that. I didn't install any additional application, but I'm already able to do the same thing. And it comes to the tracert, ipconfig, and netstat as well. Some of the previously mentioned tools, they use something like that under the hood, so it's the same thing. Also, some of the additional materials that you can look into, the HTTP basics, pocket reference book for all those status codes, maybe even the HTML, HTTP methods, verbs that you can use. Maybe TCP/IP, but that's a bit of a stretch on top of the HTTP knowledge, at least. And yeah, we are at the end of the lecture. Hopefully you liked it. And if you have any questions, just unmute and ask. Okay, I see you understood everything perfectly. And now you'll be able to understand everything that we're going to look into tomorrow when we talk about asynchronous stuff in JavaScript. And since the requests actually take time, according to HTTP protocol, we'll use today's knowledge tomorrow to actually make some of the practice oriented stuff during the lecture. Okay, guys, so thank you very much for your time and see you again tomorrow. Bye.